Okay, well, good afternoon, everybody. So my talk with Edward, my colleague here from Papua New Guinea, and Louis Gawi, who's not with us, but he's the coordinator of the Geodetic survey activities. We're going to talk about our experience in Papua New Guinea with developing a new datum there. So it's a bit of a summary in some ways of what has been discussed here over the last 3 days. So it's a bit of perhaps a nice summary in some ways because it's actually being adopted in PNG. So where is Papua New Guinea? Papua New Guinea's southeast of Thailand, north of Australia. It's the western edge of the Pacific, and it shares, the island is shared with Indonesia, with the Papuan region of Indonesia. So it's the junction between Asia and the Pacific. It's a very, very culturally diverse country. There's 840 language groups in Papua New Guinea. And until the last 150 years or so is relatively out of contact with the rest of the world, especially the inland areas and the highlands. It's a very, very difficult place for doing geodetic surveys. There are an enormous number of challenges due to the sparse infrastructure. A lot of areas are only accessible by remote airstrips or tracks. The rugged topography is a major impediment to development. The highest elevation is 4,509 meters at Mount Wilhelm. It's only just slightly less than Puncak Jaya in Indonesia and Indonesian New Guinea. So we have some major geographic obstacles. There's a photo there of the Hindenburg Wall. It's a kilometre-high cliff that straddles the western part of PNG. And road access is very limited. So we have some areas, there's 11 meters of rain recorded in record situations. And if this, of course, generates a lot of rivers that are major obstacles for transiting. So these are big challenges for getting geodetic survey work done. And also we have lots of law and order problems in Papua New Guinea. Papua New Guinea is famous for its law and order problems. We have a lot of tribal fighting, especially in the highlands, but also rascal gangs that often cause troubles in the urban areas. So that's also a bit of an obstacle for doing surveys, is that the safety of personnel is not guaranteed, nor is the safety of having the equipment not being tampered with. And notwithstanding the issues with the topography, the climate, and tribal fighting, but we have a lot of tectonic issues, being in a very, very complicated part of the world's tectonic laboratory. We're at the junction between the Australian and Pacific plates. And in between, we have a lot of microplates that are doing quite rapid rotations that are basically, it's like balls in a vise. You tighten the vise up and all the bearings move in different directions. So that's what the tectonic plates are doing. You could call it tectonics on steroids. We have some of the fastest convergence between two sites across the New Britain Trench, the fastest strike-slip boundary along the Whiten Fault. These are really extraordinary, an extraordinary setting, and also a large number of earthquakes. So we have an interferogram there from the 2018 earthquake, 7.5. So we're able to combine INSAR with GNSS measurements as a sort of a validation or a cross-validation. That's one typical one, and also some photos there of a big earthquake in 2000 that displaced a road in New Ireland, and also this leads to volcanic eruptions. So going back to Geodesy, and I'd like to sort of reinforce what Nick is saying, that yeah, we like to put in Geodesy, we like to put Geodesy as the foundation of spatial data. Data does not exist, doesn't have much meaning unless you have a geodetic foundation that forms the basis of the coordinate system on which all the other data is represented. So in Papua New Guinea, because we don't have many cause stations, we're reliant on passive classical style ground marks. These are permanent survey marks, as they're called in PNG. There's about 15,000 of them. And these marks and their coordinates basically underpin the country's spatial data infrastructure. So if we look at those layers and we expand them out into photos, so this is what the geodetic network supports in PNG, but it could also be the same for other countries in the Asia Pacific. So we're looking at it's the basis for mapping, imagery, LiDAR, mining and resource extraction, surveys for those, civil engineering, and perhaps more importantly, cadastral surveys. Defining land boundaries is a very, very important aspect of any geodetic activity. So this leads to cadastral mapping, but also monitoring of earthquake hazards and tectonics. So the current datum that we have in Papua New Guinea is already a geocentric datum. It was realised with GDA 94 in 1st of January 1994 reference epoch. So it's the same as GDA 94 basically. So we like to acknowledge the input of Peter Morgan, who was the analyst of that data, but also people like John Allman and some other OSLEAG and various other associations were involved in this. So our network has got 14 stations with ITRF 92 coordinates at epoch 1994.0, and the precision of those is about 3 centimetres. If we go back in time, the previous datum that the current datum superseded is a non-geocentric datum, the Australian Geodetic datum 1966. So again, because Papua New Guinea was under the administration of Australia until 1975, it inherited a lot of geodetic infrastructure and datums from Australia. So even though AGD 66 has been superseded for some time now, it's still actually in legislation. For instance, the Oil and Gas Act still has it as a mandated datum because the lease boundaries are defined in terms of latitudes and longitudes in the old system. If we change the geodetic datum, you also change the lease boundary coordinates, and they're not neat 5-minute blocks anymore. They're some minutes, seconds, decimals of a second. So for that reason, we have to deal with the old datum still. Our cause network in PNG is very minimal. It's one of the biggest limitations with our geodetic infrastructure, I have to say, and my colleagues also agree that we really need to have more cause stations in PNG. We have 2 IGS stations, 4 APREF stations. There's 4 national cores that are used for local positioning purposes. And it's only just in the last year that we've had the first commercial cores set up by APTELA in Leh. So we are really, really behind the 8 ball in lots of ways. We do need more cause stations. It's a matter of funding, but more pertinently, because of the problems that I alluded to in the first few slides, to have a cause station, you have to have a power supply, you have to have internet, and also security of the site. Without those, having a cause station is a bit meaningless if it's only going to run for 6 months before it gets non-functioning. Now the problem is, and the same as with Australia with its geodetic datum, is it's already age challenged. Like at the moment, the reference epoch is now 31 years plus. But unlike Australia, which is tectonically stable at the sort of centimetre level over all that time, in PNG we have a lot of tectonic activity. So since 1994, we've had over 3,500 magnitude 5 earthquakes. We've had 115 earthquakes greater than magnitude 6.5 and 14 magnitude 7.5 earthquakes. And included in that are some that are magnitude 8. So these large earthquakes create meter level displacements on the Earth's surface. So this plays havoc with the geodetic network. It introduces distortions and displacements, and it really makes it hard if you're using a PPP type GNSS positioning, which is very widespread now. A lot of people are using PPP at centimetre to 5 centimetre precision, and we get an ITRF coordinate. You need to convert that to PNG 94, transform it to PNG 94. It's getting really, really hard to do that because of all these displacements. So this was the motivation for the new geodetic datum, which is going to be called PNG 2020. It was commenced last year. The PNG government decided they were going to do it after some deliberation, and the design of it will be ITRF 2020. The reference epoch will be the 1st of January 2020. Now we're already in 2025, so there's some discussion, should we actually change it to 2025 because it might be a bit closer to the now or even in the future, like Australia had done. But the advantage of 2020 is that we already have a lot of data that straddles that epoch, but it's also aligned with GDA 2020, which is the Australian geodetic datum, and we share a common territorial zone across the Torres Strait. So it's important to maintain that continuity. And because it's a semi-kinematic datum, there's two components to it. So the operational, the backbone will be ITRF 2020 as a fully dynamic datum for all the data analysis, but it will be converted or transformed back to epoch 2020 using a velocity grid. So the primacy is going to be ITRF 2020 because of the complex tectonics and remoteness, but we will do our best to transform that ITRF coordinate back to an epoch 2020 coordinate for operational use. So there are a lot of agencies, because of the high costs in PNG and remoteness and difficulties of getting data. It's a unique opportunity to collaborate, for the government departments to collaborate and contribute. So we've had good contributions from the National Airports Corporation with their control network, NMSA with their tide gauge data and benchmark networks, and also the Geohazards Agency, Rebel Observatory, very, very key partner in this work. There's the academic group, which I'm representing of, but also the private sector. The private sector do a lot of private surveys. They do geodetic measurements, GNSS measurements. The data that they obtain is very useful because it's expensive in a remote area. If the client is going to pay a private surveyor to do some work, that data can be used by the government to improve the datum. So then you look down at the clients, and the big clients are typically the resource sector. So the big mining companies and oil and gas companies, by bringing them in as partners, they're actually contributing to the improvement of the datum, and it's a win-win situation all around. And we also appreciate the support from our neighbours. So lately we've had big support from the Australian government through DFAT and Geoscience Australia for funding the geohazard study in the Ley area where our university is. And that was done between 2022 and 2024. And there were a couple of big workshops where we had a lot of the university and government staff being involved in improving the capacity building for Geodesy in Papua New Guinea. So there's some photos there of the workshops and field work. So typical PNG setting. We have a lot of remote villages, very, very friendly people, wonderful hospitality, not like the photo I showed you first. That does happen, but otherwise people are very friendly. They're very friendly until they get angry. Like anywhere, I suppose. So the priorities at the moment might not be immediately intuitive, but really we want to improve the tectonic velocity model. So we're trying to get a bigger spread of stations where we have existing measurements to improve the tectonic velocity model. Then the next priority is urban survey control. We have a lot of development going on, and the development needs the geodetic infrastructure, but perversely, these rapid developments also destroy the geodetic infrastructure because the reliance on passive marks, these get destroyed, and it does create a bit of a headache. So this is one of the benefit of having a cause network. Then we're looking at the border with Indonesia. PNG has a big land border with Indonesia, and there's been an ongoing project with that for many, many decades now. We're looking at critical infrastructure, airports, ports, highways, telco, utilities, resource sector, agriculture, and so on. So the data analysis, this is one of the biggest challenges we've had, is to actually harvest as much GNSS data as we can. We have about 33 years of data to look at. And by analysing all that data, we can improve the velocity field for PNG to quite a good level. So those icons there are partners who've been doing a lot of the analysis over the last 30 years or so. I'd like to particularly acknowledge the Australian National University and University of California, Santa Cruz. They've done some very, very major tectonic studies in PNG, and their data has been provided to the government agencies for datum development. So this is very useful. And what we do is we get all this 33 years of data, we analyse it in a consistent reference frame in ITRF 2020, and we look at a time series, and we try and extract out of that time series an interseismic velocity from which we can build up our model, which is basically the rate of change of a position with time as the velocity. And we can build up a model over the whole country, and that is a talk in its own, really, to talk about how we do that. We don't have time for that this afternoon, but that's worth discussing. At the moment, we have limited computational capacity. We're using a weighted combination of AusPos and NRCan PPP solutions. They typically agree within a few millimeters with each other, so they cross-validate each other. So we tend to think that's quite a good, if we get good agreement, that's probably quite good, we can use it. But we're looking at other open source processing like GNAN, developed by Simon McCluskey in Geoscience Australia and his team, as something we're actively looking at. So this previous picture is obviously like, nice to have, but really that's quite rare in some areas. Often we have this situation. We have a few measurements before an earthquake, and then there's a massive earthquake, and then we might have to wait several months before we get an observation because of the logistics. So how do we get a velocity from that? That is a really big question. And we also have the issue with stability of sites. So there's a photo there of a site at Hydes. This is the big 7.5 earthquake. It basically pulverized that area, and we have like marks that are used to define the displacement, but in themselves they might be unstable. So how do you differentiate that? So this is really important to have, and I'd probably stress that for everybody here. Don't be reliant on one particular station. Have a network of local stations. So you have like a local site tie. So you actually almost have a bit like a VLBI SLR. You have your primary station, but a network of stations nearby you can use to validate and monitor the stability of that station in a local context. So that is a challenge. We need to work out what these displacements are with sparse campaign data. So that's also probably a 40-minute talk on it. So don't have time for that really. But this is some of the results. This is from the GA DFAT funded project that our university was involved with doing the field work. So we went to most of those sites shown where those vectors are. So these are velocities with respect to the stable Australian plate. So this is the area where the lay seismic zone is in northeastern PNG. So it's a convergence of 3 tectonic plates. So it's quite complex. So if we zoom in into the lay urban area where our university is, we have one of the fastest convergence rates, strain rates of any place possibly on the planet. So over the distance of 4 or 5 kilometres, we have up to 40 millimetres convergence happening per year in an aseismic setting. So this is a great concern because the recurrence rate of earthquakes on that fault system is about every 200 to 250 years. And every time that's in a magnitude 8 or an 8.5 earthquake. So it's a bit of a scary thought. So the need to densify the network to monitor the strain rate and identify whether hazards are acute is a very, very important job for us. And subsidence we measure from the network. We have subsidence not necessarily due to hydrological causes, as is often the case with urban cities, urban areas where there's water extraction happening or abstraction. This is a tectonically driven subsidence. As you can see there, as you go into the hinterland, you're getting uplift from the locking of the major fault systems. So I've already shown you this photo, but zooming in a bit more, you can see here the combination of GNSS and INSAR is a very useful technique. INSAR has some limitations, particularly if the geometry of the ascending and descending orbits are closely aligned, you don't tend to get good resolution of displacement in that particular plane. It's not very clear. So you can see there that outside the fringe pattern, which is line of sight displacement, you've got a couple of sites where you actually have very strong displacement signals that are not necessarily indicated by the interferogram. So a combination of techniques is really useful for that. So the difference between PNG 94 and 2020 is quite dramatic. A bit like Australia, it's a very fast tectonic setting. So up to a couple of meters, but not necessarily in a uniform sense because of the complex tectonics. So in a country like PNG, and I guess it's the same for New Zealand, Indonesia, Japan, Taiwan, any of these countries that have major faults, plate bounding faults go through them, we can't really use a conformal 7-parameter transformation, or the 7-parameter transformation is limited in its scope. Not only in terms of its area, but also its if it crosses into another plate, it's not really useful. So we need a grid transformation. So we're looking at NTV2 because it's widely accepted, but also using the newly developed GGXF, which is based on NetCDF, and also GeoTIFF. We also hear that a lot of people are using GeoTIFF for their models. The geoid model that we currently use is basically an adaptation of EGM 2008. So we sort of followed what Jack McCubbin was talking about. We basically got EGM 2008 and realized there were large offsets in PNG because of the mean dynamic topography. So in 2011, in a somewhat urgent requirement for a LiDAR study being done for coastal inundation studies, we had to actually make up a model that was actually relevant to sea level. So we had to apply an MDD correction to create this somewhat hybrid geoid to account for the mean dynamic topography. And in PNG, we actually have the global Mount Everest of the world's geoid. You know, between Port Moresby and Lae, we have an 87-meter geoid height, which is quite interesting. But what we want to have is an improvement of the geoid, because the geoid's only got a precision of about 20 to 25 centimeters. We need it to be a bit better than that. For a lot of applications need higher precision than that. So a national airborne gravity survey would be fantastic, but it'll be hugely costly, because as Jack was alluding to, to get an aircraft flying at 150 meters above the terrain in PNG is actually probably not really possible for all sorts of reasons. So we need to look at ways of improving the geoid, but we will also look at the HAT-LAT offset models that we saw with Cornelius. That was a very good presentation, and Evert with his talk. So this is very relevant to what we're doing. Components of the datum are going to be physical monuments and cores. We need to have more cores. But there's also legal aspects to any datum because it's a legal instrument. We need to have it, it's going to be in the Gazette, Government Gazette. And also it needs to be put into the geodetic registries, the EPSG and ISO registries so that it's actually usable. Because the software vendors, the GIS and positioning software vendors tap into these registries and they harvest those to get the data so that people can select those options when they use the GIS or GNSS. We need to make the information openly available. So we need to have an accessible database of coordinates, elevations, metadata, sketches, and our government's a signatory to the UN-GGCE. So they've agreed to have this data in the FAIR principle. Maybe if you read that with low resolution, it's unfair principle. Maybe I should have thought about that. We have a lot of people that make money out of selling PSM sketches and selling coordinates. That's not approved from now on. I think my colleague Edwin here is definitely keen to make sure this is openly available. We need to have the data available through cause portal, data portal like Australia has with the GA, but also real-time data streams for real-time positioning. And we really want the Australian AusPOS service, which is an absolutely fantastic service, to actually generate PNG 2020 and PNG 94 coordinates for submitted data. At the moment, there's a bit of a mixture of ITRF and GDA coordinates, and it's not helpful. So in order to have that, we need to have the models for those services to use. And we also need to have a lot of stakeholder involvement and engagement with all the different government agencies, authorities and utilities that will use the data. So we're looking at the ICSM as a good model for formats and guidelines. And Land Information New Zealand has probably more in common with PNG because of the tectonics than Australia has. So New Zealand is a very, very helpful country and its government have been a great friend of ours. Just wrapping up, we have a few projected CRS, coordinate reference systems. It's not Celestial Reference System in case anyone's wondering. We had this argument with Roger a lot. Why? So the current map grids is the current map grid is PNG map grid, which is similar to the Australian map grid, similar principle to UTM projection. PNG map grid will be 2020 will be the same, 54 to 58. These are designed for mapping and regional studies, but they do have some limitations. So one thing that we've developed, which is I think probably perhaps an original contribution of PNG to the global geodetic effort. And I've got a final year student who's doing this as her final year project. She's going to develop town grids for all the 30 major towns of Papua New Guinea so that we have a local projection system that has a scale factor close to unity so that it can support cadastral engineering surveys. Unfortunately, we have a lot of engineers and cadastral surveyors using UTM coordinates, but of course these don't really line up with, you have a big scale factor, which means that the ground distance does not match the grid distance, and it can be quite confusing. So we've developed a system where the local transverse Mercator will share the same central meridian as the UTM zone that it's within, So this means that the bearings between the two systems will be equal. So there's no rotation. This is also a useful aspect of it. So there's some maths there. You can download these things, presumably. I think they'll be downloadable. I won't weigh into that, but if you want to develop an LTM, you can use that as a sort of a template. If you do use this elsewhere, you might want to look at the radius. That's a general radius used in PNG. It's only an approximation, but it's good enough for a local area. If you want to do the full combined scale factor, it's a bit more involved in that. The registry, we need to have the data in the registry and have the formats, and we need to have transformation grids between the different datums that have been used. So these will be not conformal transformations, they'll be grid transformations. And the next thing is how do we use a semi-kinematic datum in practice? This is again probably a 40-minute talk in itself. Is that because ITRF is going to be the prime datum for positioning and analysis, you need to convert that to the local coordinate system and datum. So we get a position, you use the velocity model, which is interpolated from the grid to work out what that coordinate would have been at the reference epoch. Now that's the straightforward case, but invariably in a country like PNG, you'll have an earthquake between the reference epoch and the time of measurement. So there'll be models there of earthquakes. So there'll be another grid as part of the overall model where you can apply a correction for the earthquake to go before the earthquake or after the earthquake, depending on what data you're using. Often a lot of legacy data is not corrected for the earthquake, but it's still used. So this is a very similar system to what New Zealand has, what New Zealand is using. So yeah, so a bit of a headache. So there's a few different types of headaches. So you get migraine, front of the head, tension, back of the neck, stress. Then you have Geodesy, and then you have PNG Geodesy. That's a complete headache. So there's a few observations to be done over the next few months by the Geodetic section. Got funding to do some observations to tidy it up. But we hope to get the gazettal of the new datum by 2.5 months. The clock's ticking, because the 16th of September this year is a special day for Papua New Guinea, 50th anniversary of independence from Australia. And that's to be celebrated. The Australians are going to celebrate, the PNG are going to celebrate, because it was a peaceful independence. So thank you very much for your attention.